So, hello everyone, welcome back. Now we can start from where we stopped. So we have seen here basics about schematic, but let's try with a more complex example. So let's close this, what we have, and open one of the example schematics that comes bundled in every Typhoon installation. Let's click File, Open Example Model. And here, let's start with the power electronics and the grid connected converter, PQ. Let's open the TSC schematic for this. All right, we have our schematic here. So let's go through each part so you can understand what this is all about. Here in the left side, we can zoom in a little bit with this button here. Here we have our representation of the grid as a three-phase voltage source and two sets of impedances. So the two sets represent a weak grid and a strong grid, respectively. These two options are changed using this contactor. So we can, in real time, simulate the behavior for these two situations. We also have here some measurements for the grid. And you'll notice here that we have these blocks here. They are tags that allows us to connect two parts of the schematic without actually have to pass a line through the schematic. So things are more organized and readable. We also have here converter current measurements, an LC filter, and also these output switching voltage measurements for the inverter. And we have here our three-phase, two-level inverter. Let's check it out. Currently, we are using an internal modulator. What that means? This means that we receive here in the inputs duty cycles for phase legs A, B, and C. And this uses an internal triangular carrier to generate the switching patterns for this converter. But we could also change this for a digital input. So whenever we have a real DSP connected, we could just connect the output PWM of the DSP into some digital inputs and use them here for our DSP to control this converter. But for now, let's just stick with internal modulator. And in the DC part, we have just a constant DC voltage source and a capacitor with some measurements. The command of the inverter comes here from the signal processing part, coming from the modulator tag, which basically is a result of this part down here, which represents the control part of this example. Let's check it out. Here we have some measurements from grid currents and voltages and measuring power, PQS and power factor. Down here we have a PLL, which gives us frequency. And here we have the main part of the converter control. Here we generate current references based on power references and grid voltage. And this comes to the grid controller, which also receives measured currents on the system. These blocks are actually subsystems, so we can double click them, and we have other blocks here implementing this subsystem. So we can have a more organized model by grouping things in terms of their function in the system. And when we have a larger view of the system, we can understand more easily what everything is supposed to do. So this current controller runs on DQ, so it's synchronous reference frame based on the data from the PLL, and outputs here the duty cycles that are used in our three-phase inverter. Another thing to notice here is these circles. They are probes that are used for measurement of signal processing signals, so we can see them also on Hill SCADA when we are running our simulation. Another thing I want to show you is here. We can click here in Model Browser, and we have a list of all the components that we have in this model. So when it gets more complex, we can maybe find them more easily here. Okay, but now we understand the system. Let's run it. And before we can run, we have to compile this. So to compile, we have these two buttons up here. They do the same thing. They compile the model, but this one at the right with a little gear actually compiles it and loads the model to Hill SCADA. I'm going to show you later how this looks like, but for now, let's just compile this model. When we compile it, we see some messages in the message console, which give us information on the compilation process. Let's wait for the compilation to finish. All right, finished compilation. So basically, I'm just giving you a general idea of what you see here. If this is the place where if you have any problems compiling the model, this is the place where they will be shown. But more importantly, they show you how are the resources in the Hill used by this model. So you can see here that we have contactor utilization, overall weight of our electronics in each of the cores. We have memory use, and most importantly, we know that when we see here, we see that timing constraints are met, and we can run our simulation, in this case, at 1 microsecond time step. This could happen that your model is too complex for the chosen time step. And you would see here messages saying exactly what are the constraints that are not met. And if you set the simulation step to auto, he will automatically try to run compilation again with a larger time step, which consumes less resources from the Hill. In this case, timing constraints are met with 1 microsecond. We have generated our C code, and we have compiled it successfully and saved to this folder. So we have a compiled model now. How do we load it? And now is the part where we switch to our other tool, Hill SCADA. So let's open here. We can see that we can also load recently open models, but let's just load here, clicking here or here, the model we have just compiled. So we can go to Pro Electronics, the same converter, target files, and the CPD file is the one we used for the compiled model. So what we have here, now he's trying to load this model to the Hill. And before that, actually, the other button that compiles and loads Hill SCADA, it basically goes right straight into this this screen in Hill SCADA, so we don't have to open Hill SCADA and actually open the model. But right now, we don't have any Hill device connected. So what we can do is try to the virtual device. So this will basically build a virtualized Hill device that runs on the computer. and it works exactly the same as a Hill device, almost exactly. There are some differences, but the most important one is that it may not run in real time because it depends on processing power on the computer that Typhoon Hill software is running. So let's use let's use virtual device here. So you can see a message concerning the steps for loading the model. Let's wait. All right, so we have a virtual Hill running build at least. We have this model loaded, and I want you to pay attention here to the right pane at model settings. So we can see here some resources that we can use in our simulation. So double click in sources. So you remember that we could not actually set DC voltage source in the schematic because we can set it here. And we can use different types of signals. We can set a DC voltage to constant DC source. We can use sine waves with, let's say, 220 RMS volts line to neutral. We can even use arbitrary waveforms that we can load from a source, and we can use to have more flexibility in our simulation. We also have control of contactors that can be controlled by software, and we can change their state. We see here switching blocks for the inverter that can be overridden by software too. And we have our SCADA inputs, which are, as I told you, the means, a very good mean that we have to interact with simulations, so we can change its value here. And also, we have some output controls. So we have analog and digital outputs. So let's open analog. So very briefly, this is the place where you choose some of the signals in the simulation to go through one or many different analog outputs in the Hill connectors. So you can use this not only analog outputs, but also digital outputs for your actual controller to receive the signals via analog and digital outputs. Also, we can use these two buttons here to save and load these settings. So we don't have to change this every time we run a model. All right, this is one of the most important things, but another thing is, okay, how do we see what happens in our simulation? For this, we have what we call a Hill panel, Hill SCADA panel. Let's just create a new one so you can see how this looks like. We have a canvas here, and we can use all these widgets in the library so we can know what happens in our simulation. So it's very easy to use. Let's just drag and drop some here. For instance, a digital display. We can double click it. Let's say I want to show active power. So I want to show an analog signal, and I want to show P. That's it. We can use also sliders. So let's say we want this to be our references. And when you open it, you see here that this widget has a Python code. So many of these widgets have this possibility of writing custom Python code depending on the actions we do on the widget. In this case, let me show you a very simple example. I want to change active power. So we can open this code editor. We can find here our SCADA inputs, and here is our power reference. We can just insert it here. So it automatically writes the API function that we have to use to change active power. And here we know that this variable holds the value we set in the slider. So let's just do it like this. So it auto completes. We can save it. And that's how we set things up. So Python gives us a lot of flexibility. And in the widgets, we also have LEDs for showing digital signals, trace graphs for analyzing how signals change in time. We even have this capture scope. So if we want to see very detailed signals, we can use it. Let's double click it. So this works almost basically just like a real oscilloscope. We can choose some signals here. Send them to different plots. Here we set in the right trigger settings. And we also have a capture function that we can use to just do a single shot capture. But I'm going to show you all of this actually in a more complex example. So we already have a predefined hue scalar panel for this. So let me close this example and open here the standard one. So we have many widgets along with images from our schematic. So they can be obtained by exporting from the schematic editor too and be used here. You can see that it's locked. We can unlock and lock it again. So we cannot drag and drop and mess while we're using these widgets. But okay, stop talking. Let's just run and see what happens. So we see things happening here. We have a DC link voltage already being measured. We have, let me zoom in a little bit, the voltages being shown here, converter currents. We also have interaction with these grid settings, but I'm going to show you later that. Let's go here to this trace graph where we have active and reactive power. So it's a measurement. And we have these sliders here for power, active and reactive power. So we can actually change it and see the behavior here in the trace graph. So we are interacting in real time with our simulation. We can also see the resulting angles of power here in this phasor graph. That's zero reactive. And now this is in phase with voltage. Let's do the opposite. And now it's orthogonal. We just have reactive power. What else can we do? Let's open the oscilloscope here. So we can see that we have real-time representation of the signals. Let me trigger this in grid voltage, this yellow one. And we have here grid voltage and converter currents, A, B, and C. We can see them changing here as we change power in real time. All right. We also have here the converter output voltage. You can see it's a switching pattern alongside with other variables. We can choose them here in the signals button. We have a list of signals, analog and digital, if we want to. So let's check capture. I can just import settings from scope. And don't worry, you may have many questions on the details of this, and you'll be able to check the details in the other presentations throughout this week. And also we can answer your questions, and you can check the documentation hub for a description of everything I'm doing here in this demonstration. But let's go to capture, import settings. You choose a sampling rate of 1 megasamples per second. Let's capture 1/10 of a second, and let me force it. So we have captured, and we can now just analyze it very in details. So we can see here in high resolution what happens to our simulation. So it's very intuitive. Let's go back here and let's do something more interesting. Let's see how is the dynamic transient behavior of a step change in active power. How do we do this here? First of all, let's add power to the last plot, this one. Now let's trigger on a change of active power. So let me choose P as a trigger. And let me trigger this when it goes over 5 kilowatts. Let me just zero this reference here to prepare. Let me start the trigger. So it really waits for this trigger event to happen. And let's go to, let's say, 30 kilowatts, okay. So it triggered, and we have the captured data. Let's see it. So you can see how easy it is to find things we want in real time, interacting with our simulation. So we can see the behavior of our currents before and after the event. And also, we can see here how is the response of power in our converter. Good. I think this is enough for the capture scope widget. Let's go back to scope. Let's leave this as it is now. And what else can we do of interesting? Okay, let me just show you how quickly it is to simulate a fault of one of the converter switches. So let me unlock here this panel. Note that everything is running. Let me add a checkbox. Yeah, okay, a checkbox, fine. Let me edit this. So we want this to be a fault in switch. So, okay, next step, let's go to code editor and find one of our switching blocks here. Let's take this one as a top. This is one of the switches. So I want to, when I click this checkbox, when it's checked, I want to override by software, and this is going to be opened. And I just add it here. Let me just correct indentation, which is very important in Python. And when it is unchecked, let me make everything go back to normal. Well, that's it. Hopefully this will work. Let's see. Let me save this. And okay, 1, 2, 3. Yeah, that's it. Then we see in real time the behavior when this fault occurs. Let me take it out again, on and off. So this is a very good tool that we have a very intuitive understanding of what happens in different operating situations for this system. Other things that we can do, let's go up here now to this grid settings. So we can change this voltage source using the widgets too. So let's add some harmonics. We can see here that this happens also real time. Go back to per sine wave. And also we can apply some grid faults. We have some pre-programmed here. Let's go through a low voltage right through. So the grid voltage in yellow will dip during half of a second. Let's see it. Okay, again. So we saw that voltage went down and currents went up because we are controlling power here. And the way it is implemented is very, very simple. We have all the flexibility of a Python script. So we can program here what happens to which voltage, the voltage changes for how long, and we can use Python code with our Hill API to define this. You'll have more details on all the possibilities that we can do with Python code, advanced testing, all those things you'll see later on this week in this training. Okay, it's enough for this model. So let's take this a step further now. We want to go to system level. Let's see how this looks like. First of all, let me close this panel. Let me close HillSCADA, it's okay. And then let's go back to schematic editor. Let me close this grid connector example. Let's open now another example of a microgrid. And let's take this marine microgrid here. Let's open schematics. So what we have here is a simulation of a ship electrical system. This is a relatively simple microgrid. We can have way larger examples, but this one is very good for showing you the main concerns. So we have here a generator. We can look into this mask and see that we have here a machine. We also have here a battery storage. Let's check it out. So we see here that we have this battery interfaced with power electronics and all the control system here. Let's go back. We have some loads. And we have a propulsion system. Oh, sorry. Yeah. Let's go. Which is basically a machine interfaced with a drive. Okay. So, yeah, we can see here that we can use subsystems to hide complexity, and we have a more usable model for system level, higher levels of abstraction. Okay, so let's compile this, and now I will compile and open HillSCADA. No problem. So we have here some warnings. Some outputs are not connected. These are fail proofs that this might indicate that you missed something in your model. Also some outputs here concerning electrical manipulation of the system. So let's just wait for this to finish. Okay, so we are now automatically into HillSCADA wanting to load the model. But I'm going to go back just to that messages in the schematic editor. This is very interesting. So you can see here that we actually have an example of cores being overutilized. So simulation here, in this case, for half microsecond is not possible because the model is too complex. So we have a message here, timing constraints are not met, and we increase it now to 1 microsecond. And now we see that we have capability of running this model at this time step. And now we compile this model. All right. Back here, let's load to virtual device. And really, this would be exactly the same if we have a real Hill device here, except that simulation would be run would be ran in real time. All right, we load this. Let's open the default SCADA panel that we have already made for this. And now you can see something very interesting. Let me just go and play this. Here SCADA allows us to have a very intuitive interface that we can use to interact with our models and our systems. So you can have here a shape of a boat. We can go through all the systems here, double click, and have a very user-friendly interface where we can see the important variables that we want to check. So let's go generator, battery storage. We can use these dials to change very easily. And then let's check the control bridge. So the main benefit of this is that you can present this to users that are not really familiar with the details of power electronics, but are interested in the actual application of this. So here we have this schematic which has a lot of power electronics, but we can present this to someone that is going to operate the ship, and he can already interact with the simulation and give feedback. So this our tool allows to really reduce the feedback loops that we can have in our development process. So guys, so everyone, I think you enjoyed this demonstration. As I said, many details that are not explained here, you can check with, you can ask us, you can check the documentation, and you can check the other presentations. And I hope I was able to show you that we can go from this very low level of simulation to a very high level, system level of abstraction. So if you have any questions, please just ask in the GoToMeeting. And I think we are set now to a 30-minute break. And the next part will be more detailed modeling explanation on how we can build our models in the system. So thank you very much, people, and see you soon.